Alright, so this video is a demo for your R assignment number 3. So this will measure college graduate competency number 8, which is being able to communicate mathematics orally and or in written form. Question 1 gives us a scenario. It says the weights of 4 randomly and independently selected bags of potatoes labeled 20 pounds were found to be 21.0, 21.5, 20.5, and 21.2. We're told to assume normality. So part A says find a 95% confidence interval for the mean weight of all bags of potatoes, right? So this problem we're going to work through with confidence intervals, and then number 2, we're going to end up doing a two-tail hypothesis test, and we're going to use R as our technology to do this, right? So I'm gonna go split screen with my Word document and with OneNote here so I can make some notes, right? So, with number 1, right? Before we start doing finding a confidence interval, don't forget that we need to check our 3 assumptions for the central limit theorem for population means, right? So this is outlined in chapter 1, right? So we need to check our conditions. So, right, we can say first we must check that the conditions of the central limit theorem are met before calculating the confidence interval. Right? So the first condition is that we have a random sample and independence, right? So we're told that we have 4 randomly and independently selected bags of potatoes, right? So our first condition of a random and independent sample is met as stated in the problem, right? So the first condition is met. We were given that, right? The second condition is a large sample size, right? So remember, we need a large sample size n greater than or equal to 25, or we need normality, right? So our second condition of a large sample size is met with the assumption of normality, right? We're assuming normality here, so that meets our second condition. The third condition that we need to meet is having a large population size, right? So we meet the condition of a large population because it is reasonable to assume that there are, so 10 times 4, right? We have a sample size of 4, so we need at least 10 times 4, so that's equal to 40 bags of potatoes labeled 20 pounds in the population, right? So I had a typo here, right? So we're just going through meeting all of our conditions. So first condition, second condition, third condition. So all those are met, right? So don't forget we have to do that first to make sure it makes sense to continue on, right? So we check my conditions. Right, so these are met, right? Conditions are met. So now what we need to do is construct the confidence interval. So the confidence interval, right, is x bar, right, plus or minus t critical times the sample standard deviation divided by square root of n, right? This makes our confidence interval. So let me just write down my data. So my data are these four numbers. So data equals, we have 21.0, 21.5, 20.5, and 21.2. Right, so there's my data. Right, so that's all information I need to write down. So let me open up R now. Go split screen with my notepad. So we could upload an Excel file into R, but since we only have 4 data points, I'm just going to use the C command to just list, right? So I'm going to say I'm going to call this data 1 for question 1, and then for question 2 I'll call it data 2, right? So that we remember what is what. So data 1 equals, and I'm going to use the C command to type everything in, right? And we're going to use commas to separate my value. So 21.0, comma 21.5, comma 20.5, comma 21.2. Right? I'll close. Close the parenthesis there, hit enter, and there's data 1. Right? So then we need to find x bar, which is the mean of the sample. So I could let x equal the mean of data 1. Right? So here I'm naming x to be equal to that, right? And then another value we need to find is this t critical value. So to be able to find my t critical value, right, we need to find a t such that with my t distribution I have negative t and t here, and inside of here is 95% of data. Right? And remember, with the t distribution, the curves look different depending on the sample size, right? So we let degrees of freedom denote how the curve looks like. So the degree of freedom is equal to n minus 1, where in this case my n is 4, right? I have 4 things, so this would be 4 minus 1, which is 3. So I need to know degrees of freedom, right? So in R, we can find this t value, right? But what we have to do is input the data to the left of t, right? So I need to input the area to the left, and I have to know degrees of freedom. So this area to the left wouldn't be 95, right? Because we have this blue area and this red area, which total 5%. But we know the t distribution is symmetrical, so here is 2.5% of my data, and here would be 2.5% of my data. So the area to the left would be these two combined, right? So 97.5%, right? So I'm going to use what's called the QT command. Right? So in R, the QT command will give the t critical value, right? So QT, what you do is you type QT, and then parentheses, you'll type area to the left, and then comma degrees of freedom, right? Close your parentheses. So we need the QT command. So I'm going to say t equals QT then 0.975 comma 3, right? And as I type these values in, like if I hit X enter, that'll give me the mean, right? And if I hit T enter, that'll give me the T value, right? So then what else do I need? I need the s and n, right? So I can let s equal the standard deviation of data 1, right? So that's my standard deviation, and I can let n equal, and I can use the length command of data 1. So the length command tells me how many items I have, right? So I took each variable in my confidence interval and typed it in and let it equal some r command, right, in order to calculate. So now I can just reference those variables, right? So the confidence interval is going to be x minus. So I could do lower is going to equal x minus t. We need to use times s divided by the square root of n, right? So I can just type in lower, and I can find that. And then I can push the up arrow to get this command back, and I can just alter this and make this the upper part of the confidence interval and change this minus to a plus. And then I can type in upper, and we should have found both of those, right? All right, so there's my 95% confidence interval, right? So my confidence interval is, so my lower, we'd have 20.381, and my upper, so if I go to 3 decimal places, would be 21.719, right? So there's my confidence interval. So if we go back into Word, and one thing to note, at the top, I did forget to say, you hit pound, your name, and hit, R assignment 3, right? So when you're doing this for your R assignment, put that at the top, right? So I can identify the name and what assignment it is, right? And what the codes go to, right? So don't forget to put that in your R codes. Right, so we check the conditions, and now I found the 95% confidence interval, right? So I could say, using R, we found the 95 confidence interval to be 20.381, 21.719. Right, so there's my confidence interval. All right, so then part B. So does the interval capture 20 pounds? Is there enough evidence to reject a mean weight of 20 pounds, right? So I can say the following. So the interval does not contain, right? Because 20 would be below our lower part of our 95% confidence interval, right? 20 is less than 20.381. So we can say the interval does not contain 20.0 pounds. Thus, there is enough statistical evidence to reject a mean weight of 20 pounds, right? In other words, there is statistical evidence that suggests the true mean weight of potato bags labeled 20 pounds is not equal to 20 pounds. Right? Or, I mean, you could actually say, instead of is not equal to, we could say is greater than 20 pounds, right? Because we're 95% confident that my true population mean is going to be within this interval, and both of these numbers, right? Everything in this 95% confidence interval is going to be above 20 pounds, right? So we could believe, this would suggest that we would, it seems believable that the potato bags actually have a higher mean weight than 20 pounds, right? So now we need to interpret the 95% confidence interval. So we could say we are 95% confident that the interval, so our interval was 20.3381, 21.719, contains the true mean weight of all bags of potatoes labeled 20 pounds, right? So we're 95% confident that my true population mean is in this interval, right? So there's number one, right? Alright, so just add some spaces there. So number two, we have a randomly sample of 10 independently healthy people, show the following body temperatures in degrees Fahrenheit, so 98.5, 98.2, and so forth. We want to test the hypothesis that the population mean is not 98.6 degrees Fahrenheit using a significance level of 0.05, right? So we want to state the null and the alternate hypothesis for part A, right? So again, before we do this, we need to check conditions, right? So the book suggests two conditions to check for hypothesis testing for mean. So the first is that we need a random sample and independence, right? So we can say we meet the condition for random sample and independence as stated in the problem, right? So we're told that we have a random sample and we're told that they are independent healthy people, right? The next condition that we need to check is for a large sample. So remember, for a large sample, we need a population distribution that's normal or a sample size that's large, right? So the amount that we were checking was n greater than or equal to 25. So we only have a sample size of 10, and we're not told anywhere that we can assume normality here, right? So we don't have a large sample size and normality is not provided. We will check the normality assumption, right? So one thing in statistics and general practice is that we don't always know if a population is normally distributed or not, right? So in practice, I wanted to make you aware that we do have some statistical techniques in order to check normality, right? See if normality seems likely, right? For our population to come from a normally distributed, right, population. So I just wanted to make you aware. One common test is called a Shapiro-Wilk test. So this is often used for normality. So it's a test you can do in R actually, and it will give you a p-value. So it's a form of hypothesis testing, right? So we're going to have a null and alternate hypothesis. We're going to get a p-value, and we're either going to think that we have normality is met or not, right? So that's one way. Another way that's mentioned down here is a QQ plot. So this is another way to see if we believe is normality, right? So these are two common techniques used, but I think it's a little above this class, so I'm not going to go any further than just mentioning them here, right? So for this level, a common thing that we can do is we can just look at a histogram. So that's what part B I have you looking at. So if we look at a histogram, and my histogram looks, it looks kind of normal. If our histogram of our sample looks kind of normal, then we can say that we're going to assume normality, right? So if I open R back, I can come up with a histogram. So I can type in the command for histogram of data 1, and which that doesn't look right. Let me try again. Alright, so my R closed unexpectedly, so I apologize for that. So where we were on number 2, right? We were checking normality, right? So we need a histogram of our data. So I need to go into R, and first thing we need to do is I need to type in my data for problem 2, right? So I'm going to call it data 2, right? Not too creative, but it'll work. Right, so we have 98.5, comma 98.2, comma 99.0, comma 96.3, comma 98.3, comma 9. Right, so typing all these in, making sure not to make an error. Right, and I can just double check these real quick. Right, looks to be typed in right. So we got data 2 entered in, and what we were doing was getting a histogram of data 2. Right, so here's our histogram. So this histogram, looks kind of normal, right? Not too bad, right? There's nothing that really pops out like, wow, this is definitely not normal. So we're just gonna copy this, and we can paste into here. Right, and I'm just going to make this a little smaller. Right, so we could say, from our histogram below, there doesn't appear to be a red flag, right? Red flag for issues of normality. So we will assume that our population is normally distributed and continue with our hypothesis testing, right? So that's what I would say, something like that, right? So again, this is just a very basic technique to see if we have any red flags or concerns for normality, right? So, this histogram looks somewhat normally distributed, because we only have a sample size of 10, so it's not like really like it's not like really skewed or anything of that sort, right? So I would continue on, right? And again, there's better ways to do this, but this is appropriate for our level of stats at this point. So now, let's see, did I miss something? Oh, we forgot to state the null and the null and alternate hypothesis, right? So part A. So to do this, we can go to Insert, Equation, and you want to go to Script, and we want this guy, right, with a superscript, a subscript, right? So we do H. You can type in 0 for the null, right? So the null hypothesis. So if we click this down arrow, go to Greek letters, we need mu, which is right here, right? So we're testing that mu is equal to 98.6, right? That's our null hypothesis. And then if I go to script, hit subscript, then my alternate hypothesis, right? So some textbooks use an A as a subscript, or some use a 1, right, for alternate hypothesis. So you can do either one, right? So we're testing that mu is different, right? So we need does not equal 98.6, right? So make sure we answer all parts, right? So we stated the null and alternate hypothesis, but we had to check conditions first, right? So we don't want to lose sight of the question. Part B, make a histogram, check normality. Put a copy here and make a conclusion, which we did. Good. So now we're ready for step C, right? Part C. Compute the appropriate t-value and p-value. All right, so let me go back to my notebook here. Right. So I'm not sure why this goes away every now and then. Right, so that's what we did before, right? So we're ready for question 2. Right, so these are my notes for question 2. So some important things for this guy, right? We need to be able to calculate my t statistic, which is my sample mean minus mu sub 0, all divided by my sample standard deviation divided by square root of n, right? So we have to be able to calculate this. And right, so if I go back to, let me open this up, we can make some notes from the question. So I know that n equals 10, right? That's given. Alpha equals 0.05, right? What else? Oh, mu sub 0 is 98.6, right? And we already said that my null hypothesis is that mu is equal to 98.6, and my alternate hypothesis is that mu is not equal to 98.6. Right? So immediately you should be thinking I'm going to do a two-tailed test, right? So I need to find my p-value is this combined area, right? So I need to find p, right? So in order to do that, we need to figure out what the t-values are, right? So and to get t, we need x bar and we need s, right? We already know the other two criteria. So we can easily do that with r. All right, so let me close out of this histogram. We don't need that anymore. So I can say t equals, all right, so t is going to be equal to the mean of data 2. Instead of typing all these commands, let me go ahead and do this. I'm going to say let x equal the mean of data 2. So and let s equal the standard deviation of data 2. We can let n equal the length of data 2. I think we got everybody, right? So then t is going to be equal to x minus 98.6, right, divided by s divided by square root of n. Right, so if I hit t and then enter, there's my t value. Right, so I calculated t to be negative 1.65 roughly. Right? Right? So I can fill that into my Word document, right? So I calculated my t critical value to be, so t equals negative 1.65, right, using r, right? So we could say something like that. And then we could state that my p value is, and then we can find this. So the r command to find the p value, right, is pt. So we're going to use this command, pt, and then the first thing you're going to put in is your t value, and then comma your degrees of freedom, right? And we didn't calculate that. The degrees of freedom are is n minus 1, which is 9, right? 10 minus 1. So if I come here and I type in pt times t, I could actually just type t comma, and then I could do n minus 1, right? And I can refer to this because I let t be my t value, n be the length, right? I already set those variables, so we can use those here also. And I find that, right? But you want to be careful here, right? Because this actually isn't the complete p-value, right? This p-value is going from this t statistic, right, to n minus 1, right? So in other words, this found the area to the left. Right, of negative 1.65. So this area is the same as the area to the right tail. So I actually need to take this times 2, right? So if I go up 1 and then I put 2 times in front, now I will get my p-value, right? So don't forget, when you're doing a two-tailed test, we have to double the area, right? Especially if you're looking like in a table or calculating in this way, right? So my p-value is 0.132, right? I guess this would be rounded to 3, right? 133. So there's my p-value, right? So now I can go back into my Word document and say my p-value is 0.133. Right now we need to state a conclusion, right? So we can say, since my p-value of 0.133 is greater than alpha 0.05, then we fail to reject the null hypothesis, right? So in other words, what we can say is there is not enough statistical evidence to support that the true population mean of, let's see, we were looking at body temperatures, right? All right. So there's not enough statistical evidence to support that the true population mean of healthy body temperatures is different than 98.6 degrees Fahrenheit, right? So that's what we can say, right? So we're failing to reject the null, so we don't have enough evidence to conclude that the null is definitely not true, or very unlikely to be true, right? All right, so that should get you through the R assignment, right?